Swayam Prabha. Digital India. Educated India.
So, warm welcome to the 11th lecture on the subject of digital signal processing and its applications. We recall that the previous lecture was devoted to an introduction and a discussion on the discrete time Fourier transform. Let us quickly recapitulate one or two important conclusions that we drew in the previous lecture and then proceed to look at some more properties of the discrete time Fourier transform. We had seen that if you have an arbitrary sequence xn and if the summation n going from minus to plus infinity xn e raised to the power minus j omega n converges, we call it the discrete time Fourier transform of the sequence xn denoted by capital X as a function of omega. Here the dependence is on the variable omega, and you will recall that omega is a continuous variable. It can take on values continuously all over the real axis. However, there is periodicity in x omega, right. So, you will recall also that we derived that x of omega is equal to x of omega plus 2 pi for all omega. And therefore, there is a periodicity in x omega of 2 pi. We also saw that the prime interval over which x omega needs to be considered is the interval from minus pi to pi. So, what we call the principal interval. It is adequate for us to look at the discrete time Fourier transform over this principal interval of minus pi to pi, right, because it would then be repeated at every multiple of 2 pi. What is more is we are also seeing the inverse discrete time Fourier transform. We had seen that you can reconstruct xn from x omega in the following way. Further, we had also looked at a very important property of convolution. We saw that if you convolve two sequences, each of which has a discrete time Fourier transform, and if the convolution also has a discrete time Fourier transform, then there is a beautiful relationship between the convolution and the two sequences in the Fourier domain or in the frequency domain. Namely, when you convolve two sequences, their discrete time Fourier transforms are multiplied. Alright, so we showed that if x1 is convolved with x2, and if x1 and 2 respectively have the DTFTs capital X1 and capital X2, then x1 convolved with x2 has the DTFT x1 into x2. That is what we proved the last time. We had also started looking at some of the properties of the discrete time Fourier transform. We saw that the discrete time Fourier transform viewed as an operator is linear, right. So, we saw that if you think of the DTFT as an operator, then x1 and 2 being operated upon by the DTFT to give capital X1 and 2 implied that alpha x1 plus beta x2 had the DTFT alpha capital X1 plus beta capital X2. What is more, We had also seen that if x had the DTFT capital X, then if we time reverse, it leads to a frequency reversal too, or essentially frequency negation. That means every positive frequency becomes a corresponding negative frequency, and that's obvious because time reversal amounts to rotating in the opposite direction, and therefore every omega is replaced by a minus. Of course, we also came to the same conclusion algebraically. Now we take further the discussion of some properties. For example, we ask what happens when we complex conjugate. So, but before that, let me ask if there are any questions at this point before we proceed. Are there any doubts or questions that need to be clarified before we proceed to discuss a few more properties? Yes, there's a question. Okay, that's a good question. So the question is, we had said that the whole idea of reconstructing Xn, in fact, let me go down to the inverse DTFT. The question is, when we discussed this idea of inverting the DTFT, we said the idea is that you take each component, multiply by a so-called unit vector in the direction of that component, and instead of adding, now you integrate over all components, because these components are a continuum. Omega is a continuous variable. And the question is, how could we call, how could we talk of a unit vector in the context of e raised to the power j omega n, since e raised to the power j omega n does not have magnitude 1, or for that matter, it cannot be made to have magnitude 1. Now, let me clarify exactly what we are saying here. What we are saying is that when we use this idea of multiplying a component by a unit vector, it is of course true for a finite dimensional space. But here we are talking about an infinite dimensional space. So we can take inspiration from that idea, but we may not be able to use that idea exactly, right? There has to be a slight modification. And the modification is that here what we assume happens is that, you see, we are assuming all the while, remember, that x omega converges. That means there is an infinite summation that converges. That need not happen. So under convergence, under x omega converging, what we are saying is all the information has been retained in the x omega, omega going from minus pi to pi, and the approach that you would use to reconstruct is similar to what you would do for finite dimensional spaces. That means take the component and multiply it by a so-called unit vector in that direction and add over all such components. Now, unfortunately, here multiplication of e raised to the power j omega n by 1 by 2 pi doesn't really make it a unit vector. But what we are doing here is akin to what you would do in a finite dimensional space, namely multiply a component by a unit vector and add over all such components. So the idea is similar, but the idea of a unit vector cannot be taken exactly from a finite dimensional space to an infinite dimensional space here, right? So although what he is saying is that essentially e raised to the power j omega n by 2 pi is not really a unit vector. Its magnitude, or if you take the sum squared of the magnitudes of all the samples, it doesn't converge. But the idea that you can multiply components by vectors in different directions, suitably normalized, is being employed here. And what we did later was to take inspiration from that idea, but to derive the factor 1 by 2 pi exactly by algebra, right? So later on we used algebra to come exactly to the conclusion that you needed a factor of 1 by 2 pi there. So it's not correct really to call it a unit vector, rather it may be more appropriate to say that we take inspiration from that idea of multiplying components by unit vectors and adding over all components, but the conversion of a vector to a unit vector essentially involves normalization by a constant. We allow that normalization by a constant using the factor 1 by 2 pi here. That is the way to understand this, right. So, when you go from finite to infinite dimensional spaces, there are certain catches of this kind which you need to deal with, right. So, for a greater or deeper understanding of this, I would recommend going into functional analysis, but that is not the objective of this course. What we are doing here is to take inspiration from that idea, and we know that you probably would require a factor kappa 0 here. We saw from algebra that factor turns out to be 1 by 2 pi. We later on proved this relation exactly, right. We later on derived this inverse exactly, and there we saw that the factor of 1 by 2 pi was required, right. So, that is the way to understand this. So, in general, it is a good idea to use geometric insights to understand several signal processing ideas, but when using geometrical insights, one must be careful to distinguish between certain things that happen obviously in finite dimensional spaces, which do not generalize exactly to infinite dimensional spaces, but what you know in finite dimensional spaces gives you an idea of what to expect in an infinite dimensional space, and you then have to tune or to correct what you expect by looking at the basic algebra. Okay. Is there any other questions? All right. So, in that case, we will proceed then with the discussion of some more properties of the discrete time Fourier transform, namely, let us look at what happens when we complex conjugate. So, if you know that the discrete time Fourier transform of xn is capital X of omega, what is the discrete time Fourier transform of x bar n is the question that we would like to ask. Now, that is easy to do. Let us calculate the discrete time Fourier transform of this. It will be summation n going from minus to plus infinity, x bar n e raised to the power minus j omega n. And of course, we can rewrite this. See, what we do is essentially we want to take the bar all above here. So, how would we do that? You could of course remove the minus sign and take the conjugate here. So, this is the same as e raised to the power j omega n complex conjugated, and therefore, I have now, of course, when you take a sum of complex conjugates, it is the complex conjugate of the sum. So, I have x n. Now, here I can rewrite this as e raised to the power minus j minus omega times n and the whole complex conjugate, which turns out to be x minus omega the whole complex conjugate. So, complex conjugating without time reversal amounts to taking a negation on the frequency axis and complex conjugating once again. And this leads us to a very interesting conclusion. If I take xn to be a real sequence, then x bar n is equal to xn, that is what you mean by real, and that means x minus omega bar is x omega. So, what we are saying is if you take corresponding frequencies omega and minus omega, they are related by complex conjugation. That means on the omega axis, if I take corresponding positive and negative frequencies, the discrete time Fourier transforms are the complex conjugates of one another. Now, what is the physical interpretation of this? You see, if you look at how the signal is formed, so to speak, if you look back at the inverse DTFT, It says that x of n is 1 by 2 pi integral from minus pi to pi x omega e raised to the power j omega n d omega. Now, of course, we reinterpret this as before as saying that we take so many different omegas, actually all the continuum of omegas for omega going from minus pi to plus pi. For each of these omegas, you can think of a pair of omegas, one plus omega 0, the other minus omega 0. They come together. So, x at omega 0 contributes x omega 0 times e raised to the power j omega 0 n. Minus omega 0 contributes x of minus omega 0 times e raised to the power minus j omega n. So, you have a corresponding complex rotating phasor, one rotating clockwise and the other rotating anticlockwise with respective frequencies omega 0 and minus omega 0. And what we are saying is that the corresponding components are complex conjugates. They have the same magnitude, but the opposite phase or the opposite starting angle. In other words, what we are saying is if you plot x omega 0 and x minus omega 0, they would look like this. They have the same magnitude and they have exactly the opposite starting angle. This is the symbol for angle or starting angle of phase. So, you can visualize if there are two vectors, if there are two rotating phasors like this beginning here at t equal to 0 and here, and if this one rotates in a counterclockwise direction and this one in a clockwise direction, they will always add up to a sinusoid, a cosine wave. Their imaginary parts would always cancel and their real parts would enhance or be doubled. That is what we are saying here. So, every property of the discrete time Fourier transform also has a corresponding interpretation that we must understand, right. It means every pair of corresponding positive and negative frequencies have the same magnitude, but opposite starting angle, and that is illustrated very clearly from how we see them coming together to form a real signal here. Now, let us look at a few more properties of the discrete time Fourier transform. One important property is what happens when we multiply. That is in some sense dual to convolution. Let me explain the meaning of the word dual. So, in other words, if I have x1 and 2 with DTFTs capital X1 and 2, what is the DTFT of x1n, x2n? That is the question that we are asking. Now, I will spend a minute in explaining the idea of dual here. We are kind of having a foregone conclusion, we are trying to use our intuition to come to a conclusion before we actually arrive there. There is one very common principle that is useful in many contexts in the Fourier transform, and that is that very often the roles of time and frequency can be reversed. Now, in continuous time and in analog frequency, this is exactly true. So, one can show that one can more or less exactly reverse the roles of time and Hertz frequency in properties. However, in discrete sequences and the discrete time Fourier transform, this is true in a slightly more extended sense. It is not true obviously. For example, what we saw was that when we convolve two sequences, we are multiplying their discrete time Fourier transforms. Now, duality would tell us that you could reverse the roles of time and frequency. That means that when you multiply two sequences, you expect some kind of convolution to take place in the frequency domain. But it is not obvious what kind of convolution. That we will need to do with a little bit of algebra. We broadly understand that we expect some kind of convolution. That is what duality says. But we need to put down exactly what kind of convolution. To arrive at that answer, let us actually consider a product. So, here we are. So, consider the DTFT. Now, of course, we have assumed that both x1 and x2 have their own DTFTs and that this converges. We are assuming, otherwise it has no meaning to discuss this. All that we do is cleverly replace one of them by their inverse DTFTs. So, we write down x2n, for example. You could do it the other way too, but we will write down x2n as, now here we can't write omega because you already have an omega there. So, you must use another variable of integration here. Let us use the variable lambda. Is that right? So, we simply replace one of the sequences by essentially write the sequence as an inverse DTFT of its own DTFT. Now, we substitute that. So, here we are. That becomes summation n going from minus to plus infinity x1 n by 2 pi integral minus pi to pi, and you see we realize that we could as well take the e raised to the power minus j omega inside here. It does not do any harm at all. It is a constant anyway with respect to this. It is a constant with respect to lambda, so I can push it inside. And now I can interchange the summation and the integration. And I can combine these two terms. And there I am. This becomes 1 by 2 pi integral from minus pi to pi summation on all n x1 n e raised to the power minus j omega minus lambda times n multiplied by x2 lambda d lambda. So, here we have something very interesting. What we have inside the curly bracket here is essentially the discrete time Fourier transform of x1 n, but evaluated at omega minus lambda instead of at lambda or at omega. You have just evaluated that discrete time Fourier transform at a different value. Is that correct? So, there we are. We are saying this is 1 by 2 pi integral from minus pi to pi capital X1, but evaluated at omega minus lambda and x2 lambda d lambda, and recognize that this is very similar to what you expect a continuous time convolution to be. So, it looks like a continuous variable convolution. there is only one little catch. A continuous variable convolution should have run all over the independent variable axis. So, here lambda is a continuous variable. So, it should have taken you all over the lambda axis if you were to convolve the continuous functions capital X1 and capital X2. But you are restricting the convolution to one period. You have restricted the convolution to the period minus pi to plus pi. In fact, we do not really have to insist upon the interval minus pi to plus pi even in the inverse discrete time Fourier transform. In the inverse discrete time Fourier transform, we can take any contiguous interval of 2 pi. So, if we are really very fond of it, we might take the interval from 0 to 2 pi instead of from minus pi to pi. That is because from pi to 2 pi you have just the same thing that you have from minus pi to pi. If you are even more insistent on doing something unusual, you could start from pi and go up to 3 pi, whatever you please. Any contiguous interval of 2 pi is fine, and that is true here as well. So, one must in general say in this expression that you need to calculate this integral over any interval, any contiguous interval of 2 pi. It could be from 0 to 2 pi, it could be from minus pi by 4 to 3 pi by 4 if you like, or I mean, whatever you prefer. So, or minus pi by 2 to 3 pi by 2, right. So, it should be actually pi plus pi 3 pi by 4. So, so it could be from minus pi by 2 to 3 pi by 2, it could be from 0 to 2 pi, or it could be from minus 2 pi to 0, whatever you please. Any contiguous interval of 2 pi is fine, right. Anyway, this is what is called a periodic convolution. It is a periodic convolution of two periodic functions. Capital X1 and capital X2. Remember, both these DTFTs, capital X1 and capital X2, are periodic functions. Now, if you did actually write down the expression of convolution as you have done here, but you tried to evaluate this integral going from minus to plus infinity, of course that integral would diverge, because both of the functions are periodic. This would be a sum of the integral over every period, and if any of them is non-zero, that sum would obviously diverge. So, it does not make any sense when you have two periodic functions to calculate the convolution by integrating over all the independent variable axes. It only makes sense to calculate over one period, and that is exactly what we are doing here. Remember that in this expression, both x2 of lambda and x1 of omega minus lambda for any fixed omega are both periodic. Of course, x2 lambda is periodic with period 2 pi, x1 omega minus lambda is also periodic with period 2 pi. And how do you get x1 omega minus lambda from x1 lambda? Let us just spend a minute in doing that. So, just to take an example, suppose you happen to have this from minus pi to pi for x1 lambda. I mean, let me assume for the moment that x1 lambda has 0 phase. So, we will say that the angle of x1 lambda is equal to 0 for all lambda, and we have shown the magnitude here. Let us assume that this is the kind of x1 lambda we are dealing with, just for simplicity. How would x1 omega minus lambda look? Essentially, it would look with this occurring at omega. And of course, always remember that you have periodic continuation here. There is periodic continuation there, and there is also periodic continuation here. Also, whatever you see here, let us mark it as script A, is going to be seen as its own reflected version here. Let us call it A prime. And what you see here, let us call it script B, is going to be seen here, script B prime. There is also a reflection. You see, you can come to this conclusion in two steps. When you replace lambda by omega plus lambda instead of omega minus lambda, when you replace it by omega plus lambda, you are going backward by omega. And then when you replace lambda by minus lambda, you are making a reflection. So, what was at 0 would have gone to minus omega when you replace lambda by lambda plus omega. And then when you replace lambda by omega minus lambda, you are switching the lambda sign of lambda, and therefore, what is at minus omega now comes to plus omega. What is after minus omega goes before plus omega, and what is before minus omega goes after plus omega. And that is how we come to the conclusion that whatever was after this would now appear before this in reflected form. Whatever is before this would appear after this again in reflected form. This is the relation between x1 lambda and x1 omega minus lambda. Now, let us take an example to illustrate this idea. Let us take the very simple discrete time Fourier transform, which is 1 between minus pi by 4 and plus pi by 4 and 0 else, and we will assume that the discrete time Fourier transform is 0 phase. So, in fact, let us take this to be both x1 and x2 of omega. Of course, x1 and 2 omega plus 2 pi is equal to x1 to omega for all omega. And we will assume that angle of x1 to omega is equal to 0. So, essentially it is 0 phase, and the magnitude is 1 between minus pi by 4 and plus pi by 4, 0 outside. Let us find out the inverse discrete time Fourier transform of this. All right. Now, of course, how do we find out the inverse discrete time Fourier transform? We multiply this by e raised to the power j omega n and integrate over omega from minus pi to pi, simple. So, we have x1 or for that matter 2n is integral from minus pi to pi x1 respectively to omega e raised to the power j omega n d omega divided by 2 pi, and this of course boils down to 1 by 2 pi integral from minus pi by 4 to pi by 4 1 e raised to the power j omega n d omega. This is a very easy integral to evaluate. In fact, it takes us only a minute to evaluate it. This simply becomes now, please note, I have written this. Do we need to put a condition here? Yes, indeed. What is the condition? The condition is that n must not be equal to 0, provided n not 0. Now, when n is 0, what does it become? When n is equal to 0, this becomes 1 by 2 pi, and the integral is simply 1 d omega. So, essentially pi by 4 minus pi by 4, which is pi by 2. Is that correct? So, therefore, this is valid only when n is not 0. So, there we are. So, x1 or 2n is 1 by 2 pi e raised to the power j pi by 4n minus e raised to the power minus j pi by 4n by jn for n not equal to 0, and it is very easy to see that this becomes sine pi by 4n divided by pi n for n not equal to 0, and it is equal to pi by 2 divided by 2 pi for n equal to 0. Now, we ask, what is the discrete time Fourier transform of x1n into x2n? What do we expect it to be? We need to convolve the discrete time Fourier transform of any one of them with itself. So, we take the lambda axis, we put here, of course, we let us first just draw one of them. So, this is just one of them. And we can visualize the other. So, let us visualize the other. And kind of expanding it a little bit. Let me draw them on the same scale, so to speak. Now, what do we need to do? We need to multiply these two and to integrate over one period, and we can choose that period to be between minus pi and plus pi. How much is this interval? This interval is pi by 2. So, let us assume that this tip has reached, you see, now you must see, take the analogy of the train and the platform, right. So, you have this. The only catch here is now, instead of the train having people standing at discrete locations, people stand all over the train. That is the continuous time situation, right. So, here we are, here these are the people on the platform, these are the people in the train, omega moves, right. Now, suppose this point has reached here. What is the situation? Of course, this is going to be repeated at every multiple of 2 pi. But luckily, when this point reaches here, the trouble would have come from the next such square, isn't it? How far is the next such square? 2 pi away from here. That is very far from. So, it's even if this point is here, the next of these squares is not going to clash with this. Is that right? So, what we are sure is that one time only one square clashes with one square here. that I leave it to you to verify. You will never have a situation where two such squares clash with this one square here. Okay, I leave it to you to verify that. That follows from the fact that you have only a pi by 2 interval of spread. Anyway, so what would happen as omega moves from a point where omega plus pi by 4 is equal to minus pi by 4. You see, when this point is here, omega plus pi by 4 is equal to minus pi by 4. In other words, omega is equal to minus pi by 2. And at that point, this, so you can visualize this comes here and it moves as omega moves in this way. So you have more and more of this square overlapping with this square here, or this rectangle. And as omega moves along this, the area increases linearly. The area is obviously equal to this height into the base which overlaps, and that base increases linearly with time. So right from the point where this is here up to the point where this has reached here, there is a linear increase, right? Afterwards, as this point, you see, so I mean, no, a slight correction. Right from the point where this has reached here up to the point where this. So let's go back to this discussion here. We begin from the point where this edge has reached here. When this edge reaches here, up to the point where this edge reaches here, there is an increase of area. And the area goes to a maximum when this whole rectangle overlaps with this rectangle here. Afterwards, this edge begins to move away, and this edge starts to approach this one when there is a linear decrease. What is the maximum area? The maximum area is when these two rectangles overlap entirely, and that area is of course pi by 2 multiplied by 1. So we have the following shape for the convolution. So the dTft of x1n times x2n would look like this. It would start when omega plus pi by 4 is equal to minus pi by 4, or omega is equal to minus pi by 2, and it would end when omega minus pi by 4 is equal to plus pi by 4, or omega is equal to plus pi by 2. At 0, it would take the maximum. That is when omega plus pi by 4 is equal to pi by 4. There would be a linear increase here and a linear drop there, and this height reached would be pi by 2. This is how the dTft would look. Now, this so-called dual result that we have here is very important later when we talk about the effect of windowing on sequences, or when we try to design finite impulse response filters with windows. We shall gain a lot of insight into what happens when we truncate an impulse response by using this idea of multiplication of sequences. So it is not without application or without reason that we are discussing this property. Anyway, so much so for that property. But this property at the moment gives us something equally valuable and interesting. Let us write it down. Yes, there is a question.
You said that there won't be any problem because the period is only minus pi by 4 pi by 4.
That's right.
If it was from minus pi to pi, then
That's a very good question. So the question is, here we didn't run into any trouble, or the whole convolution became easier because two rectangles didn't overlap at once. Each of those dTFTs is periodic. So what we said is, I left it to you as an exercise to show that when one of the rectangles was interacting with the basic rectangle between minus pi and pi, no other rectangle interfered because the other rectangle was too far away. What would happen if this were not the case? Well, if this were not the case, you have to account for rectangles that come at once carefully. So in fact, that's a very good question, and let me leave it to you as an exercise to do the following. Exercise. Let the two DTFTs x1 to omega take the following form. Let them be 1 between minus 3 pi by 4 and plus 3 pi by 4. And of course, angle is 0. They are 0 phase. And of course, you know that x1 and 2 have the DTFT capital X1 and 2 as before. The exercise is obtain the DTFT of x1n, x2n. And in fact, I will also leave it to you as an exercise to show that x1 or 2n comes out to be sine 3 pi by 4 n by pi n for n not equal to 0 and 3 pi by 4 by pi for n equal to 0. Anyway, here when we do this exercise, we will have to worry about more than one rectangle overlapping at once. So you have to carefully account for the rectangles that would overlap with the basic rectangle each time you move, right? Anyway, as I said, let us come to one very important special conclusion of this so-called multiplication principle. And that is as follows. Let us look at what happens when we put omega equal to 0. So we have x1 to n with DTFTs x1 to omega. And we know that x1n times x2n, if it does have a DTFT, it would be essentially 1 by 2 pi integral minus pi to pi x1 lambda x2 omega minus lambda d lambda. Now, let us in particular take x2 complex conjugate n. You see? So, if x2n has the DTFT capital X2 omega, what is the DTFT of x2 complex conjugate n? We know what it is. It is x2 minus omega complex conjugate. And therefore, if you choose not to multiply x1 and x2, but x1 and x2 conjugate, what do we have? x1n, x2 complex conjugate n would have the DTFT 1 by 2 pi integral from minus pi to pi x1 lambda. Now, here you would have to write x2 omega minus lambda, but it would be lambda minus omega complex conjugate d lambda. Because you reverse or you change the sign of the argument and you also complex conjugate. Is that correct? Now, in particular, look at the consequence of this for omega equal to 0. Look at the consequence of this at omega equal to 0. It says that the dTft of x1 n, x2 complex conjugate n evaluated at omega equal to 0 is 1 by 2 pi integral minus pi to pi x1 lambda x2 lambda complex conjugate d lambda. Isn't that true? Because in this expression all you are doing is putting omega equal to 0. Now we have a very, very interesting statement. What indeed, what do you mean by the dTft of x1, x2 complex conjugate evaluated at omega equal to 0? The dTft of x1 n, x2 complex conjugate n evaluated at omega equal to 0 is simply summation n going from minus to plus infinity x1 n, x2 complex conjugate n e raised to the power minus j0 n, which is summation x1, x2 complex conjugate over all n. And this is known to us, we are familiar with this. This is our familiar inner product of the sequences x1 and x2. It's a very interesting result. Why so interesting? Let's put them down together, then we'll see why it's so beautiful. We are saying summation n going from minus to plus infinity x1 n, x2 n complex conjugate is 1 by 2 pi integral minus pi to pi capital X1 lambda, capital X2 lambda, complex conjugate d lambda. Now notice the similarity in these two sides, the left hand and the right hand side. Similarity in spirit, if not exactly in expression. What do I mean by the similarity in spirit? Look at the left hand side. On the left hand side we are saying multiply corresponding samples, but of course the second one is complex conjugated, and add over all such samples. On the right hand side we are saying multiply corresponding points on the frequency axis, but the second point is complex conjugated. On the left hand side, because we are dealing with a discrete independent variable, we are saying add. On the right hand side, because we are dealing with a continuous independent variable, we are saying integrate. On the left hand side, because we are dealing with an independent variable which runs all the way from minus to plus infinity, we are saying add from minus to plus infinity. On the right hand side, because we are dealing with periodic functions or the discrete time Fourier transform, we are integrating only over the principal period. But on both sides, we are multiplying corresponding components or corresponding points on the two functions. The second one is complex conjugated, and we are integrating on the right hand side and adding on the left. We are putting them together. We are putting together all such sums. In other words, we are bringing out an equivalence between two inner products. And now we need to reflect for a moment on this. In fact, we have seen something very interesting in this lecture, and we shall dwell more on this as we begin the next lecture. Thank you.